Today we're going to learn about projectiles launched at an angle. This will be different than what we have learned about previously for projectiles because we are going to have some initial vertical velocity now. I think the best way to learn about projectiles launched at an angle is just to do some practice problems using the formulas that we've already come up with. So here's one of my favorites. Why don't you copy this problem down in your notes and then we will solve it together. You can go ahead and pause the video, and then once you get the problem copied down, we'll go through it. Here it is. A scared kangaroo once cleared a fence by jumping with a speed of 8.42 meters per second at an angle of 55.2 degrees from the ground. If the jump lasted 1.4 seconds, how high was the fence, and what was the kangaroo's horizontal displacement? And there's even a little hint here. The time of the maximum height was half of the total time. That's one way to solve it. We're going to use that fact. The parabolic motion is symmetric. So there goes my kangaroo. So copy the problem down and then we'll start up again once you get it copied. All right, so here is our diagram again. And we are going to solve it using the gummies method. So we will write down our givens, our unknowns, and the model that we're going to use here first. For givens, we are told that the initial angle of the kangaroo's jump was 55.2 degrees from the horizontal, and it was at a speed of 8.42 meters per second. We are also told that the time of the entire jump was 1.4 seconds, and because, as we mentioned, the jump is from the same height to the same height with projectile motion, so it should be symmetric on both sides. So it should take about half of the time to reach the maximum height as it would to reach for the whole jump. So there is what we are given. The unknown is what is the height of the fence. So that is our vertical displacement at the time when the kangaroo is at the highest height. We're going to assume the kangaroo just barely cleared the fence. And so delta y at the time of when the kangaroo was at its highest point, that is 0.7 seconds, that is going to be the displacement. We also want to know what is the displacement for the entire trip. Our model is going to be a projectile launched at an angle, which means we're going to use constant velocity in the horizontal direction and constant acceleration in the vertical direction. So what we'll do is define the horizontal displacement. Once we know the horizontal velocity, we'll know it for all the time. And we actually know the total time that the jump took, so we can actually do that one right now. For the vertical displacement, we're going to need to find the vertical displacement using the time that we were given. We figured out that it's going to be half of the time for the total flight, but we do need to calculate this time the initial vertical velocity, so we can also plug that into our equation. And for our acceleration, we're going to use the worldwide average of a negative 9.81 meters per second squared. And we need to use trigonometry to find the initial velocities. We know the initial velocity was at 55 and some degrees from the horizontal, so we'll need to figure out what the components of that initial velocity are. Remember, the only triangle that comes into play is when we try to figure out what the initial velocity was and its components. The path of a projectile is not a triangle, it is a parabola. So don't try to draw some big triangle and say that's the motion of the projectile. All right, let's carry it out. Let's implement our plan. There is our triangle to calculate the two components of the velocity at 8.42 meters per second with a v0 y in the vertical direction and a vx in the horizontal direction. Well, we know that Vx over V naught is the cosine of the angle. So therefore, the Vx must be V naught times the cosine of the angle, meaning if we plug in the numbers now that we have an equation, the initial velocity in the x direction, which is the only velocity in the x direction, is 4.81 meters per second. The initial velocity in the vertical direction, similarly, becomes V naught times the sine of the angle, which becomes 6.91 meters per second. All right, so we can get the horizontal motion now. We already know the velocity then in the horizontal direction, and we know that the time for the entire jump was 1.4 seconds. So therefore, the horizontal distance must be the horizontal velocity times that 1.4 seconds, or 6.7 meters. For the vertical motion, we'll plug in the numbers that we know here. V naught y is 6.91 meters per second, we just found out. And remember, we're trying to find the displacement when the kangaroo is at its highest point, so therefore our time now is 0.7 seconds, and our acceleration is a negative 9.81 meters per second squared. Plugging in those numbers in that equation gives us a vertical distance of 2.43 meters. Now we should evaluate our solution. We found that our kangaroo has jumped 6.7 meters horizontally and a height of 2.4 meters vertically. Those are actually realistic numbers, believe it or not. These kangaroo can really jump sometimes, especially if they're frightened.